Okay, we're going to get started here. There may be a couple more people coming in from East Campus. Okay, welcome. So I am absolutely delighted to introduce Professor Anil Seth. Professor Seth, did his BA in Wesleyan University, so in physics, astronomy, and music. Okay, great. PhD in astronomy at the University of Washington under Paul Hodge and Julie Dalcanton. So that was on the origin and evolution of late-type galaxies. Professor Seth, I want to just call you Seth, Anil or Professor Seth, then went to Harvard as a postdoc before moving in 2011 to the University of Utah in Salt Lake City. So there are a couple of things that Professor Seth has been doing at the University of Utah along with astronomy. So I want to point out that he is the founder and the leader of the Bryce Canyon National Park Summer Astronomy Outreach Internship. Yes, nailed it. And I've known about this internship for quite a while because I have many undergraduate students that get really interested in this. And so I'm kind of send them that way and write letters for this. And the other thing I wanted to point out that he also helped develop the world's first dark skies studies minor in the world at the University of Utah, which is really interesting. We got to talk about it yesterday. But the reason I invited him today, or we did, is because I've known about his work since grad school on galactic nuclei in particular, but he is a world expert on the evolution and kind of structure of nearby galaxies. And today he's going to be talking about some really exciting results to do with Omega Cen and the discovery of what would be, I think, the lowest mass supermass black hole. For the students, the lowest mass supermassive black hole. That would also turn out to be the closest example of a supermassive black hole that we have to date. So thank you so much.
All right. Awesome. It is great to be here. I haven't been here in like 20 years. So I think the last time I had a friend who was a PhD student here a long time ago. And I haven't been here since then. I also did summer camp right below Long's Peak, so I have the Front Range skyline is very I enjoy a lot. So it was great to see that and great to visit everyone today. I'm going to be talking to you guys about Omega Centauri. It's this beautiful picture right here is of that object. And I'm going to talk to you about how it's our nearest galaxy nucleus and what exciting things we can learn from it. And this black hole result that Anne-Marie was alluding to is kind of been the most exciting thing I think that I found been part of in my career. So I'm really excited to share it with you. This is actually my first time giving a colloquium on this topic, so hopefully it won't be too rough. I have some past group members whose work I'm going to be talking about and current group members. My two graduating PhD students, Christian Hanna, Callie Clontz, a postdoc Pramorta Wong, whose work you're going to see. I've been working for a long time on the centers of galaxies. And in particular, as I was a PhD student, I was actually working on resolved stellar populations of nearby galaxies. And I had this image in my PhD thesis data. And there was this like football-like thing at the center of this nearby galaxy. You can see individual red giant branch stars here, but there's this crazy bright little football-shaped object at the center. And I got really curious about that. And it turned out that this is an example of a nuclear star cluster. Its density is something like 1 million times higher than the underlying galaxy disk at the center of this galaxy. And I wanted to take a poll. How many people have heard of nuclear star clusters before in this audience? OK, great, good. It helps me calibrate. Oops. I wrote a review with Nadine Neumeier, my closest collaborator on a lot of this work. few years ago on nuclear star clusters and what we've learned about them. And one is that most galaxies have nuclear star clusters. So the left-hand plot here is showing what fraction of galaxies when we observe out in the universe, both early type, meaning galaxies without gas, red and dead galaxies, and late type galaxies, those with gas. What fraction of those have nuclear star clusters at their center? And you can see that over a wide range of galaxy stellar mass, it's well over half of them do have these dense, massive star clusters at their centers. And those dense, massive star clusters fairly strongly correlate with the mass of the galaxy they live in. So bigger galaxies have bigger nuclear star clusters. These objects are, probably several different formation mechanisms for them, but there's kind of two that have been very popular for a long time. One is that through dynamical friction, where a dense cluster will be moving through a galaxy, this material will collect in its wake, and it'll be dragged into the center by that material. That's called globular cluster in spiral. So basically, like massive clusters in a galaxy will end up at the core of their galaxy. And this is how we can get these dense clusters at the centers of galaxies. And then, of course, you can form stars directly in the center of the galaxy. Gas can also make its way to the centers of galaxies. And recently, we've learned that there seems to be somewhat of a transition where lower mass galaxies tend to, their nuclei tend to just be a collection of multiple, probably globular clusters that have collected at the center of that galaxy, while more massive galaxies have a larger contribution of this kind of star formation channel. And the Milky Way is no exception to these kind of typical galaxies. This is the very central region of our galaxy. It's taken with the Spitzer Space Telescope. Of course, there's like 30 magnitudes of extinction to the center of our galaxy, so we can only see it in the infrared. And that dense ball that you're seeing there is just like the one that I showed you earlier. It's a nuclear star cluster. This one has about 30 million solar masses of material in it, effective radius of around 5 parsecs. And of course, if we zoom in all the way to the center, this is the central tenth or so of a light year, there's this famous movie that I'm sure many of you have seen of the individual massive stars at the very center of our galaxy orbiting a location that has a very faint radio source in it, Sag star. And this is evidence of a black hole at the center of our own galaxy. So at the center of this nuclear star cluster, there are stars that are orbiting and bound to a black hole. And those stars are moving really quickly. They're moving at something like 5,000 kilometers per second. Their orbits can give us the mass enclosed in their orbits, and that's 4 million or so solar masses. Feel free to ask questions as we go along. And this is, of course, an example of the other object that we find at the center of many galaxies, supermassive black holes. We think they are nearly ubiquitous. Almost every massive galaxy has a supermassive black hole. And they're well known to regulate the formation of stars in galaxies. This creates a correlation between the galaxy's stellar mass, in the amount of stars in a galaxy, and the size of its black hole. One of the interesting things, and this is a famous image of M87, and including the Event Horizon Telescope image, which, of course, Jason was involved in too. One of the interesting things about these supermassive black holes is that we really don't understand their formation mechanism. We have folks in the audience who've worked on this before, and I'll talk a little bit more about it in the future. But that is still an unknown question, is how these supermassive black holes form. Okay, these objects both live at the centers of galaxies. They also coexist. We know about their coexistence in more than 20 galaxies. That's kind of a small sample, really, when you think about it. But these things are really only easily visible very close to us. They blur into this, dense central parts of galaxies farther away. And it turns out that actually all the galaxies that we know about that are below about 5 times less massive than Milky Way we've only found black holes in galaxies that have nuclear star clusters in them. And this is a lot of my own group's work on determining dynamical masses of black holes in nearby galaxies. There's a general trend. This is the ratio of black hole to nuclear star cluster mass as a function of galaxy stellar mass. And you can see there's this huge amount of scatter, but a general trend that more massive galaxies put more of their central mass into a black hole, while less massive galaxies seem to put more of their mass into a nuclear star cluster. Not totally understood why that would happen. Of course, there's lots of interesting consequences here, too. Black holes and nuclear star clusters interact. In particular, their formation might be tied. One of the possible formation mechanisms is that during the formation of a dense star cluster, you can form, say, a supermassive star. That supermassive star will explode and form a large black hole that could form the seed of the supermassive black hole that grows into what we see today. And then stars from the nuclear star cluster can get very close, be put onto plunging orbits, get disrupted. And those are really exciting events, both because they're easily visible and also because they can probe galaxies where we don't know whether there's a black hole there. If we see one of these events there, that's a very, very clear signature of a black hole. And this is actually work that one of my PhD students is doing right now, Christian Hanna, on looking at nearby galaxies and their nuclear star clusters and really getting good assessments of the expected rates of these tidal disruption events. And then, of course, if we have black hole mergers, which we think happen in galaxies, that can actually destroy a nuclear star cluster as two black holes come together and scatter away all the stars in the nuclear star cluster. Okay, so another thing that happens, we think, is that sometimes smaller galaxies fall into big galaxies. And when that happens, the material from the outer parts of the galaxy is typically lost first. And over time, more material will get the tidal forces of the larger galaxy will eat away more and more and leave behind just the central core of the galaxy. Just the kind of nuclear star cluster of the galaxy is left behind. And this other material will kind of mix in with the halo of a galaxy over time, get phase mixed, and eventually you won't be able to distinguish it in the way that you can in this movie. But this core of the galaxy can be left behind. And this was a simulation showing that process, which ended up on a real object, which is actually 120 million solar masses of stars in a dense, crazy dense star cluster that has a 20 million solar mass black hole in it. So about 10 years ago, we found this black hole at the center of that object that I just showed you the movie of, and through an adaptive optics observation of its motions. And that object, we are pretty sure, is a stripped galaxy nucleus based on the fact that it has this black hole. It also has many other properties which suggest this must be the case. And we've now looked at a bunch of objects similar to this. Well, not a bunch, 6 objects similar to this, and we found black holes in all of them. And these are all really, really massive objects. Those are the easiest ones, of course, to observe. But every time we've looked, we found a massive black hole in these type of objects, these compact clusters of stars. We call them ultra-compact dwarfs, which is a horrible name, that are orbiting around large galaxies. And theory work has also shown that basically at this highest mass range, these dense star clusters, because these nuclear clusters grow to larger sizes than ordinary globular clusters, basically all these objects we think are probably stripped galaxy nuclei. And so, one of the things we've been interested in is how much less massive can these get. And so this kind of brings me to the main event of this talk, which is Omega Centauri. We think this is our nearest galaxy nucleus, and I'll highlight why. So one is, for a long time, we've known that Omega Centauri has a really wide range of heavy element abundances of metallistes, and that is not ordinary for a globular cluster. Basically, it has much wider spread than any other globular cluster. The only other comparable one is actually known to be the core of a dwarf galaxy that's falling into the Milky Way. The Sagittarius dwarf has a nuclear star cluster, which has a similar spread in metallicities. But otherwise, it's unique amongst the galactic globular clusters. And with the advent of Gaia, is there a laser pointer maybe here? Maybe not. Okay. Well, in the right panel there, with the advent of Gaia, what I'm showing you is the orbital properties of stars in our galaxy, which is the kind of background, and then globular clusters and stars that were associated with this merger event that we now call, really horribly, the Gaia-Enceladus sausage. So this GES merger we think was the single largest contributor to the single largest merger event in the Milky Way's history, and it happened a long time ago, roughly 10 gig years, maybe plus or minus a gig year or two. And you can kind of see why. Well, this is showing you the orbital energy and the angular momentum. And this material has very low angular momentum, but it's actually mostly counter-rotating. And Omega Cen is also counter-rotating. And it has a lower energy because we think it was dragged inwards through to dynamical friction. And so this is pretty strong evidence that this is a good candidate for the galaxy that was the host of this nuclear star cluster. So Nadine and I, about 5 years ago, started a new project to kind of do a thorough study of this. And there's a bunch of people who've been involved in doing the real work on this proposal. This proposal is a kind of a comprehensive study of the center of Omega Centauri with Hubble and with VLT-MUSE, which is an integral field spectrograph. We essentially get a lot of spectra, and I'll show you that in just a second. The data that we've gotten is the spectroscopic data is there on the left. We have 100 pointings of this MUSE spectrograph. And on the right, there's been an incredible amount of Hubble Space Telescope data, and we got that red ring of observations that allowed us to measure stellar motions for the stars across the whole central region of the cluster. So I have a couple of cool data movies. I love data movies. Okay. Everyone prepare themselves. You see these stars? They're going to move to a color magnitude diagram, where we've actually moved the stars to their correct position on the color magnitude diagram. And then that's from HST photometry. And then here are the spectra that we get for every one of these stars. We have a spectrum that looks like this. You can see here's two stars that have very similar overall luminosity, but have very, very different colors. And those different colors are happening because they have extremely different metallicities. One is metal poor, one is metal rich. And you can see that very clearly in the spectra. This one has very few features. This one is very feature rich due to the number of heavy elements in the atmosphere of those stars. And this is work by Selena Nichai, who reduced all this data and very heroic work. And the other data set is of this Hubble Space Telescope images. And it turns out that there was this initial observation back in 2002 of the center of Omega Centauri. And then when the not new at all anymore, Wide Field Camera 3 started, they decided to use Omega Centauri, the core of Omega Centauri, as a calibration target. So they observed it every couple months for many years, from starting about 2009, and it's ongoing. So there's this really, really incredible data set. And I stole this entirely from, I think, the Goods survey. Like, I saw this video that they had, and I was like, this is super cool, we'll make it. And you can see there's a bunch of different filters. There's more than 500 observations, individual observations at the center of Omega Cen. So really incredible data set. And then the data set that we proposed for appears right at the end as this ring of outer observations. And when we found out we were going to get that data, we started a PhD student, Max Haeberle, on looking at the archival data as well as the new data that we were going to get to measure all the proper motions of the stars in this cluster. And this shows you that central region of the cluster, the central a few parsecs of the cluster. And what you can see is that we have up to about 500 images near the center. Very consistently, they're taking all these different rotations. And from that data, we can get incredible precision on our measurements of the individual motions of stars. It's about less than a kilometer per second median errors. And that is way below the 25 kilometer per second dispersion at the center of this cluster. So we're really able to resolve the motions of the stars extremely well. And of course, we also have precision photometry in many bands. So that's also helpful for a number of things I'm going to talk about. So we have a couple science cases that we've been applying this data to so far. And this is really ongoing work. We just finished the catalogs in this last year. And then are plumbing the most exciting stuff. And the most exciting thing is this hunt for a massive black hole. So I'm going to profile that first. And then I'll talk about Omega Cen's formation history, which was actually the original goal of the project. And we have results on that, too. So people have realized Omega Cen's an exciting target for a long time. I'm not the first. And there's been a long controversy on whether Omega Cen hosted a black hole. And people did dynamical modeling of this. And there was conflicting answers. Two papers from 2010, one by Eva Noyola, said, yes, it's a 47,000 solar mass black hole. Very cool. There's almost no other black holes known in this mass range. On the other hand, Roland Vandermarle and Jay Anderson wrote a paper that said, no, we've done our dynamical modeling. There is no black hole there. Maximum mass is 12,000 solar masses. These things are clearly not consistent with each other, right? And this is exciting because, as I mentioned, there's very few. If we just think about the number of black holes we found versus black hole mass is a very cartoon-like plot. But basically, there's this giant gap of 3-4 orders of magnitude where we haven't found any black holes at all. And the candidates we have are questionable. Like none of them, and I say this as someone who's published results on intermediate mass black holes myself, none of them are really secure. If you like, you could always find another reason other than a black hole for the signature that you see. And so this question is really strongly related to this open question on whether how supermassive black holes form. So this is a figure from Mar Mezqua's paper on black hole seeding and growth. And this there's kind of 3 different mechanisms that people have looked at. There's more than 3, but 3 broad categories of mechanisms. One is this direct collapse black hole, which forms the most massive black holes and is probably would result in very rare seeding of black holes into the universe. The lowest mass option is that just the first stars that form in the universe form a little bigger. They form black holes from them, and those are seeds. And then the third mechanism is that through dense cluster formation, there's several different ways that you could potentially form intermediate mass black holes. And observing these intermediate mass black holes then therefore kind of gives us a little bit of a constraint on this. It provides this kind of minimum mass of the seed mechanism by how far down we see black holes. If POP3 stars are growing to become supermassive black holes, we should see intermediate mass black holes stretching from the stellar mass black hole range all the way through the supermassive black hole range. Whereas if almost all the black holes are being formed from direct collapse black holes, we would just expect to see no intermediate mass black holes at all. And also the number density can constrain this mechanism, because these mechanisms, even though none of them are like full theories in the sense that you can actually simulate them from start to finish or anything like that, they do have some predictions for number densities. So that's why this is interesting. But what makes it hard is a couple things. One is when you look at an image of the central regions, even that top right image of the central region of Omega Centauri, and if I asked you to point to the center, you would just choose the central pixel maybe, but there's nothing obvious about where the center is. So this was one of the problems between these two papers. They used different centers in their modeling. Different by 10 arc seconds. pretty big difference. That's about the size they were of this bottom left-hand panel. So they were different by about that same size. And the other issue is the nature of the dark mass in the cluster itself. So this dynamical modeling, you have to bin together lots of data. You can see here there's binned data points at various radii. And it turns out that you can have either a bunch of stellar mass black holes that have fallen towards the center of that cluster through mass segregation, or you could have an intermediate mass black hole, and both of them would provide you with a very similar overall velocity dispersion curve in this cluster. Essentially, the stars would move about the same speed near the center, whether you had a bunch of stellar mass black holes or a single intermediate mass black hole. And so a bunch of people had noted this, a couple papers here, but this bottom right figure is showing not just the velocity dispersion, but the whole distribution of velocities at the center of this cluster. And there's 3 lines shown, and the line that is the red line and the blue line are the intermediate mass black hole and the stellar mass black hole models. And what you can see is they all predict this. The stellar mass black hole predicts this very sharp cutoff, and the place where it cuts off is the escape velocity of the cluster. So basically, you don't expect to see any stars that are moving faster than the escape velocity of the cluster. They've all left. The intermediate mass black hole model, on the other hand, there should be some stars that are tightly bound to the cluster. Those stars should give you the signature of an intermediate mass black hole and be visible in this kind of histogram of masses. So these were both simulations, but the prediction was that there should be quite a few of them. We should be able to observe them if there was really a 50,000 solar mass black hole there. And there wasn't. So we didn't think there was a black hole. Yeah. So those fast stars are the signature of an intermediate mass black hole. When Max made this catalog of stars, he looked up at the velocities of them, and he found that there was this cluster of stars right at within the central few arc seconds that were all moving faster than the escape velocity of the cluster. And because we're in the mountains, and I know that we all appreciate a good walk in the mountains, I'll note that this is a picture taken in Sexton, Italy, a day before Max found his fast stars in his data. And then that last day of the conference, he showed us the very early version of this plot, and it was really exciting. Yeah. So this is the fastest star. It's moving at 113 kilometers per second. The escape velocity is around 60 kilometers per second. So this thing is almost double the escape velocity. It's also very close to the best determined center of the cluster previously, within an arc second. And you can see the individual measurements there. So each colored dot there is an individual Hubble Space Telescope image where we've measured the position of this star. This is a very faint star. And so there's relatively large error bars, but you can, I think, all agree that this star is moving up and to the left. You can actually see it from the images. It moves about 2 pixels in 20 years. And that is a large signal. So we have 7 of these objects. And the first question we had is, could this just be a random chance agglomeration of Milky Way foreground stars? Stars that are nearby to us, their proper motion, even if they're not moving that fast, can appear very fast if we assume it's at the distance of Omega Cen. And there's a couple different arguments why we don't think this is true. One is that they all follow along the main sequence of the cluster. So the left-hand panel shows the color magnitude diagram of the cluster, and the stars are labeled A, B, C, D, E, F, G from centralmost outwards. And you can see especially the 4 central ones are faint, but they're all along the main sequence. And the fact that they were so faint was the reason why they weren't found previously. So someone had already published a proper motion catalog of this, but it wasn't nearly as deep as the one that we created. On the right-hand side, it shows the density in fast stars. That's a log plot. So there's a really large overdensity of stars at the center here. And again, the center was actually the center, the best determined center of the cluster based on number counts of stars. And you can see that outside of about 10 arc seconds, the density of stars that are moving fast meets exactly the background level that we expect from Milky Way models. So, and it's flat. So there's basically none of these stars moving, all the stars that we see outside of the central 10 arc seconds or so are probably Milky Way foreground or background stars, and only these ones are consistent with being part of the cluster. And the chance of a superposition is 1 in 100 million, so very low. The other thing is, maybe these stars are just, there's stellar mass black holes around, maybe there's a star moving around very quickly, but the problem with that is that to be moving around that fast, the period has to be quite short, and in fact, it would be less than the 20-year period of our observations for any reasonable stellar mass black hole. So we don't think these are binary periods. We actually see straight line. We don't have any 3 sigma acceleration detections from any of our observations. So the escape velocity gives us a minimum mass. So to keep all these stars bound, if we assume that they're bound to this intermediate mass black hole, we can take the amount that they're above the escape velocity as a minimum mass on the black hole. And you can see that in this top right panel. It shows the escape velocity as a function of radius. And the solid lines show if there was no black hole there. And the dashed lines show a black hole of 8,000 solar masses, which is the minimum mass that we get. And the right-hand line shows a mass of 40,000 solar masses. And even if you remove 1 or 2 of these stars, we get very similar limits. So even if 1 of them or 2 of them was a foreground contaminant, we would still get a very similar lower limit on the black hole mass. Yeah, so it doesn't. It basically, you can think of like each star constrains to stay bound at its position. There's some combination of black hole masses and offsets that allow it to stay bound. And like the minimum, if they're in plane together, if there's no projected distance separation, provides you the lowest mass that would keep it bound. Yeah, so, but no, because there's more than one star and they're not at the same location. So at any given location, so what this map, you can kind of see these left 4 panels show the combination of location and minimum mass for each individual star. But if we make the assumption that all these stars are bound to the same black hole, then we get that right-hand panel, which is the combination of all those minimum masses. Yeah, great question. Any other questions here? OK. So the significance of this result is, from my perspective, pretty high. It's the strongest evidence yet for an intermediate mass black hole. Like I said, I work on signatures myself of intermediate mass black holes. And X-ray signatures, all of those things, there's very few objects where we really have a lot of confidence that what we're seeing is an intermediate mass black hole. Supernova can create broad lines that are similar to broadline AGN, in a single epoch of observations, and there's lots of different ways that you can go wrong. This would be the nearest massive black hole to us. It's about 5.5 kiloparsecs away. That's closer than the Milky Way center. And it's the second black hole with multiple bound companions. And so this shows the contrast between the S stars, the central cluster stars in the Milky Way, and these stars in Omega Cen. Omega Cen is much less dense than the nuclear star cluster of our Milky Way. And there's this really amazing nuclear starburst that happened within the last 10 million years in our Milky Way that is just completely absent, of course, in Omega Cen. So the stars are much, much brighter, too. We're going down to way subsolar luminosities. The ones at the center of the galaxy are way brighter than the sun. So really different situation. There's probably another 100 or 1,000 stars that are directly bound to the black hole that we could watch oceans of if we could go faint enough. The other thing to mention in this is that because the black hole is about a factor of 100 lower mass the vectors here I've shown are 20 years for the fast stars in Omega Cen and 2 years for the galactic center. And the fact that they have similar magnitudes tells you that that's roughly a factor of 100 seems to be about right. So we're, of course, trying to do better on the mass. We just had a minimum mass that we gave a kind of maximum mass based on simulations of around 50,000 solar masses. We're working on trying to do dynamical modeling and including both a central black hole component and stellar mass black holes. And right now, this is work being done by Ranuccia Picchetti. And we're finding, I would say this is still very flexible and work in progress, but finding a best fit black hole of around 15,000 solar masses. If we just use the fast stars and only model the presence or absence of the fast stars, we can actually use that to create a dynamical model to constrain the black hole mass. And that gets us a mass of around 32,000 solar masses. So this thing is definitely in this intermediate mass regime. But what exact mass is still, I guess, a little bit, if you made me pick one, I would say maybe 25 or something like that would be my choice. So, of course, we are hoping to follow this up. I have a cycle 3 near-spec proposal that unfortunately won't be scheduled until next summer, but the data will hopefully come next summer to get radial velocities of these stars. They're faint, and so from our MUSE data, we're not actually able to resolve them. So we can get radial velocities. There's actually MUSE data for one of the stars, and this shows the gray lines are orbits that are possible with just the proper motion, and the black line is the motion, the orbit that's possible with the radial velocity known. So hopefully that'll help us constrain the mass of the black hole better. If we can get accelerations and radial velocities, then we will be able to solve this problem fully. There is already cycle 2 JWST imaging. That is a picture of that imaging. It's really beautifully deep. Rather than getting signal noise of 5 on these stars, we get signal noise of like 120. So really big difference. And that allows us to centroid much more accurately and should allow us to get accelerations if we get several epochs of JWST data going over the next few years. If you're on the TAC, be kind. And we're also hopefully going to hunt for material around the black hole. So of course, we would love the way, one of the biggest problems here is we don't know where the black hole is. And if we were able to find an accretion signature of that black hole, it'd be great. I didn't mention it, but one of the other reasons people didn't think there was a black hole in Omega Cen is people looked really, really hard. They spent 30 hours of ATCA time and 200 hours of Chandra time staring at the center of Omega Cen, and they found nothing. And I also say not quite nothing. This is their 30-hour ATCA image. There's actually a 2 sigma source at the center. And we're hoping to get ALMA data that might allow us to detect that at 5 sigma. And also the JWST data that we're getting potentially could allow us to look at the near-infrared emission of this black hole. This, for those of you who are black hole accretion aficionados, this thing is the faintest black hole in the universe. It's 10 to the minus 12 or lower of the Eddington ratio. So it's like a trillionth of the Eddington ratio. Crazy. I don't know why. I don't know why it's so pathologically bad. I'll mention a previous result by Ranuccia Picchetti, who was my former student, that we also in M31's most massive cluster have found evidence for a black hole. That black hole is around 100,000 solar masses. And we've, I would say this is not nearly as strong evidence as the evidence I've shown you earlier today for the black hole in Omega Cen. But we have compared models with a distributed version of distribution of stellar mass black holes versus a point source model. And the point source model is moderately preferred. And so this kind of brings me to like the larger implications of this in terms of this, the kinds of work that I really care about, which is the demographics of black holes and whether IMBHs, how common are intermediate mass black holes in the universe. We have, I would say, 3 strong candidates of intermediate mass black holes below 100,000 solar masses at this point. All 3 of them are not at the centers of galaxies. All 3 of them are off nuclear sources. the one that I haven't talked about so far is this HLX1. It's a hyperluminous X-ray source that goes through state changes, like a high soft to low hard state change. That gives us a pretty good idea of what its mass should be based on analogy to X-ray binaries, and it's about 10 to the 4 solar masses. And it is apparently in a star cluster off the disk of this galaxy, something like a globular cluster or a stripped nucleus. So I think it is very possible, maybe even likely, that a majority of these intermediate mass black holes are actually hiding in stripped galaxy nuclei, not at the centers of present-day galaxies. And one way of thinking about that is just how many relative of these objects are there? Is there more present-day galaxy nuclei, or are there more galaxies that have had their surroundings stripped off? And I think this is a plot of that from the Virgo cluster that my former postdoc Karina Fogel did. You can see the black line is the current galaxy nuclei. The blue line is the number of probably stripped nuclei, although with not perfect evidence. And as you get to lower luminosities, it's very possible that number outstrips, essentially the number of stripped galaxy nuclei is larger than the number of present-day galaxy nuclei in this kind of dwarf galaxy regime. And if we just look at the local group, so our nearest neighbors, we have 3 or 4 less than 10 to the 5 solar mass black holes. I say this, there's a couple of the detections which are less solid, I would say, but there seems to be 3 or 4 less than 10 to the 5 solar mass black holes. And there are 3 greater than million solar mass black holes in the local group as well, with Andromeda being the heaviest, almost 100 million solar masses. And I think that what's shown on this graph is a black hole mass function, the number density of black holes per unit volume. And this is a very small volume and very small number statistics, but I think that it's very likely that the black hole mass function is at least flat down to this kind of 10 to 4 solar mass range. And I think that that's really good news for the LISA interferometer, because if these objects exist, they will be, and they merge, then LISA will be detecting them. And that's pretty exciting. So that's kind of everything I have on the black hole. I'm happy to take more questions on it if people have them before I move on to the. OK. I feel like the lighting's just a little too low here. All right. But then my pretty pictures wouldn't look as pretty. So the Omega Centauri is weird in lots of ways. One of the ways in which it's weird is stellar populations are extremely varied. So not only are there these wide ranges in metallicity, but there's also light element abundance variations, including helium abundance variations that we think are larger than basically anywhere else we know in the universe. So it's this very unique environment where there's stars that seem to be helium enhanced to almost double their primordial level. Wild. There's also all these light element abundance variations that seem to be reflecting material that has been processed in hot hydrogen burning. So basically like CNO cycle-like material is escaping and getting incorporated into stars within the cluster. Okay, and this happens to some extent in lots of globular clusters. It happens to crazy extent in Omega Centauri. It's the most extreme example of this. Because of all those abundance variations, it makes it very, very hard to measure ages in this cluster. So you guys have probably mostly all seen isochrones before, right? And these isochrones have turn-off points where the stars stop burning core hydrogen, evolve onto the red giant branch. And that happens at very different locations depending on for instance, the helium abundance of the stars. And helium abundances are almost impossible to measure for individual stars. So this makes it extremely hard to get to an age measurement. And there's been a really wide range of age spreads claimed for the cluster. Obviously, these stars can't have all formed instantaneously. They have an order of magnitude variation in metallicity. So we know right from that this can't have been just a single burst of star formation. But how long did it last? What was the process that these stars formed under? And there's been a really wide range of claims. So we have the best measurements, I think, available for any age, for the ages of stars in this cluster. And this is enabled by a couple things. One is that we have metallicity measurements for every star. So that eliminates some ambiguity in the age, because if we know what set of isochrones to use. So that's what this left-hand panel is showing you. It's the metallicity of each star. And it's in this region of that we call the subgiant branch, which is most sensitive to the age of the cluster. And it turns out that if we use the right filter combination, a red filter combination, the helium abundance variations actually overlap at this region of the CMD. So you can see on the right-hand panel, the red dashed lines and red solid lines are the two different helium abundances. And on the main sequence and on the red giant branch, they're completely different. But right on the subgiant branch, they cross over. And there's this amazing coincidence that allows us to relatively unambiguously measure the age of individual stars. We also have new isochrones that were run for this project that incorporate a known trend of the overall carbon plus nitrogen plus oxygen abundances of the stars. And this is work that was done by Clontz, who is my PhD student finishing this year, working in Germany for the last couple years. So these age measurements we can use the Muse metallicities and their error bars. And then we can use this precise HST photometry to associate an isochrone with these data. And we find a mean age. This is an individual star's measurement. And we find a mean age of all 8,000 stars that we're able to measure of around 12 gig years, and an individual age years of around 0.7 gig years. So this is really, many of you may not know this, but sub-gigayear ages for stars is really, really hard to measure. There's like very few measurements like this that exist. So really great, exciting new things. And so here is the kind of full set of results, binned in decades or like deciles in metallicity. So we have 800 stars in every bin. And you can see that as a function of metallicity, there's a clear trend of mean age. And then if you look on the right-hand side, you see that plots the full age metallicity distribution. You can see that it's a bit more complicated a picture. That the mean age trend isn't all that's there. But here is what the mean age trend is. It ranges from about 12.5 gig years to around 10.5 gig years. And the spread in ages increases with metallicity. So at higher metallicities, stars formed over a longer period of time. The coolest thing is this feature. You can see right in the middle of the metallicity range, there's a pretty clear bimodal feature in the histograms. And you can see it on the right-hand side. There's this valley of, or this kind of stream, we call it, of stars that occupy the bottom left edge of that plot. And that structure is telling us that at a given metallicity, there was more than one location where stars formed. They were forming at different times at the same metallicity, or at the same age, they're forming at different metallicities. So this is telling us that there can't have been just one site of star formation in this cluster. And this more metal-rich system, that orange line, is actually a line that's been fit to the globular clusters in this dwarf galaxy, Gaia Enceladus, that we think Omega Cen was the nucleus of. So if a bunch of those clusters gathered together at the center through dynamical friction, we'd expect material along roughly that line. The metal pore stream is very consistent with self-enrichment. Essentially, that stars are forming from gas that the previous generations of stars are letting off. And we see features like this, like in our Milky Way's age metallicity relationship. The weird thing is that if this stuff was forming at the nucleus and all the globular clusters were around the outside, it's really weird that nuclear material is actually more metal poor than the material that's forming around it. So the physical picture of this is still not totally clear to me. But it's very exciting to see this kind of clear result where we see very clearly two sites of formation. One way that we can try resolving that is through abundances. So these individual stellar abundances. And my postdoc, Pramod Long, is using a machine learning model trained using Apogee, Galat, and Lamost to try applying this to our Omega Cen Muse data. So we have data for hundreds of thousands of stars, but we can really only do abundances for the brightest, say 10,000 or so of them. And what you can see on this right panel is actually the sodium abundance and the oxygen abundance. And this is a classic diagram in globular clusters where we see this anti-correlation of these two quantities. And the gray dots are previous high-resolution spectroscopic measurements, and the red dots of like 800 stars, and the red dots are our measurements of 6,000 stars. So this allows us to increase this sample of stars where we know these detailed abundances and hopefully tease out the picture of how these different components formed. We'd also like to be able to measure the helium abundances. I mentioned these are very important. They also give us a clue on what's going on for these multiple populations in the cluster. And this top left plot is a very confusing plot. It's called often a chromosome diagram, but it's really a color plot. So it's taking, on the left axis, it's actually a combination of 3 filters. On the x-axis, it's a combination of 2 filters. And those it's basically the color differences between one sequence and another, a reference sequence and another. So it's this kind of pretty weird diagram, but encapsulates a lot of information. And in particular, the light element abundances affect the y-axis. The nitrogen abundance really moves stars upwards along the y-axis. A helium enhancement actually moves stars primarily along the x-axis. And there's not much else that moves it significantly along the x-axis. And so this is very sensitive to the helium abundance variations. And so we're actually using this to measure the helium abundances. And we can see that we get helium abundances of about, so the primordial helium abundance is like 0.24. So we're getting enhancements of almost double the helium abundance. And those seem to rise as the metallicity rises and then plateau at some higher level. This is all pretty obscure. Like, I remember listening to George Wallerstein when I was in grad school, and he would talk about barium, and I had no idea what barium meant. I understand that's probably what many of you are feeling. So why do I think this is exciting? I think there's actually potentially a picture that ties all of these things together. So there's one of the scenarios for forming these intermediate mass black holes, and the seeds of the massive black holes we see today is that during the initial star formation events in the universe, very dense gas is turning into stars. You get these stellar mergers where basically before a star can evolve off the main sequence or anything, a new star comes in and bloms onto it. It keeps kind of puffing out, and you end up getting these puffed out stars. And those stars have a lot of stellar winds, and they may be fully convective, so that the material that's burning at the center is actually getting ejected out into the cluster, potentially forming new stars. So that would explain our very large helium abundance variations, very large light element abundance variations. And then at the same time, when that thing ends its life, it may end its life as an intermediate mass black hole. And if that were to happen, then the finding that we have of this black hole at the center of this cluster would be expected, right? So this is definitely not science, right? Like this is a beautiful picture. It would be really nice if it were true, but I think this is what gets me excited. I'm like, I see this like possible solution to this very disparate data set. Before finishing up, I'll just mention 2 more things. One of the things we're working on is looking for microlensing events from stellar mass black holes within the cluster moving in front of a star. So this is an injected event and what that would look like in our data. I think we're close to having a final list of potential candidates there. The other thing that we're working on is trying to find binaries from our astrometric measurements. So the left-hand side is from photometric measurements over time. The right-hand side, we're trying to find binaries, astrometric binaries in this cluster, some of which have already been found in a recent paper. But I think there's many more to be found, including hopefully black hole binaries. And one of the reasons this is interesting is because there's a lot of theories that suggest that all of the LIGO events that we've observed so far, the binary black hole events, have been coming from the cores of dense star clusters. And if that's true, then Omega Cen is our best bet of finding the black hole population at the cores of those clusters. And if there's no black holes there, then that I think provides some skepticism on whether that's really what's going on for LIGO. I would say, the fact that there's something like 10,000 black holes claimed to be at the center of Omega Cen, based on models, we've observed 0. I would love that number to be 1. The other thing is there's this counter-rotating core that Anne-Marie is really excited about. The velocity in the radial velocities we see the center of this cluster is actually counter-rotating relative to the larger scale pattern of velocities. And why that is, and the black hole, by the way, is at the plus symbol there. So why that is a little bit uncertain still. Yeah, that's it. Thank you.
Okay, great. I know we started a few minutes late, so if anybody has to leave, it's totally fine. I'll take questions, or I'll just take over and ask questions. Damn it. Kirk?
What's the scale from black hole?
Yeah, so we can simulate what the black hole acceleration should be. And right now they're kind of at the 1 sigma level. Like we'd expect them to be about 1 sigma with our current measurement. Or 1.5 sigma, something like that for the closest stars. And it really depends. There's so many different things it depends on. But the fact that we don't detect accelerations is not constraining right now. No, if you sit on JWST TAC, you'll find out that there are only 3 years before we can measure accelerations, because JWST is so much higher signal noise. So yeah, I probably shouldn't say that. I'd probably de-anonymize something. But. Yeah. Yeah. Yeah, I mean, we don't know yet is what I would say. One of the interesting things that we've been kind of thinking a lot about is that the number of stars in 3D at the center of the cluster is very different from the stars that we actually see projected along the line of sight, because the core is so flat. It makes that very ambiguous, like what the radii of the stars that we see along the line of sight. And so I think that there's actually probably a pretty strong signature here that is being washed out. And the fact that we're seeing anything means it has to be a fairly strong signature in a subsample of stars that are actually intrinsically close to the cluster, within the central half parsec or third of the parsec. Whether those are a boundary layer, I think Anne-Marie's theory is that it's a recoiling black hole. So there's lots of there could be a binary intermediate mass black hole, which would apparently potentially induce rotation. So there's lots of ways to make this happen, but I think it's a very exciting dynamical problem. Yeah. Yeah.
Yeah.
Yeah, I would say I would rate my surety that it's a nuclear star cluster quite high, because it just matches so many of the other features that we see in other nuclear star clusters, right? Like the range of metallicities. Whether it's Gaia Enceladus' nuclear star cluster, I would be a little less confident of. Maybe I put first one at 3 sigma, I put the next one